Okay, so we're going to talk about confusing the inverse and Bayes' theorem today. Okay, so to do this, we're going to build a two-way table to work from. And this is going to be a two-way table for like a pregnancy test. Okay, so this is going to be a positive test and a negative test. So this means that the test says you are pregnant, the test says you're not pregnant. And then what's the reality? Are you pregnant or are you not pregnant? And given the testing group, we're going to say that there were 80 positive tests for pregnant people, 5 negative tests for them, 3 positive tests for not pregnant people, and 11 true negatives, right? All right, so we're going to have 4 events here. We're going to say that A is a positive test result, B is a negative test result, C is that you are pregnant, and D is that you are not pregnant. And where the confusion comes in is that, let's say you have A given C. This is not the same as the probability of C given A. Okay, so here's what's going on here. The probability of A given C, right? So given C, C is that you are pregnant. There are a total of 85 pregnant people here, right? And 80 of them, so this is the probability of A given C, 80 of them are pregnant. So that means that experimentally here, the probability would be 0.941, which is 94.1%. If I look at its inverse, right, the probability of C given A, well, A is that you had a positive test result. There are 83 people who had a positive test result, and 80 of them were pregnant. So that's pregnant given a positive test result. And that works out to be approximately 0.964. These two values are not the same. Now, there is a pathway between them, and this is what we're going to call Bayes' theorem. Okay, and Bayes' theorem, we're going to look at in a moment here, says that these numbers are related, but they are not the same. Okay, so Bayes' theorem says that the probability of x given y is the same as the probability of y given x times the probability of x over the probability of y. All right, so let's look at our example here. We know from our calculations a minute ago that the probability of C given A was 80 out of 83. And we also know that the probability of A, right? So there were 99 people in our subject test, and 83 of them were pregnant. So that's the probability of just being pregnant at all. The probability of C is the probability of, A is getting a positive test. Take that back. The probability of being pregnant out of all of this was 85 out of 99. So that's the probability of being pregnant. Now, let's see. According to Bayes, the probability of A given C should be the probability of C given A times the probability of A over the probability of C. Well, let's see. C given A is 80 over 83. The probability of A is 83 over 99. The probability of C is 85 over 99. Well, if I look at my math here, the 83s here cancel, so this is 80 over 99 over 85 over 99. Okay, so to divide is to multiply by the reciprocal. So 80 over 99 times 99 over 85. The 99's cancel, gives me 80 over 85. And that's the probability moments ago that I did find for the complement of A given C. So using these two additional probabilities, I have a pathway to go back and forth between these two numbers. Now again, they're not equal, but there's a way to go back and forth between them, and that way is what we call Bayes' theorem. All right, so there you go. That's the confusion of the inverse and Bayes' theorem.